So in this video I'm going to talk about my advanced machine learning project. Um, so I named it ResPose. It's right now private. I will make it public. I'm in the AML project branch. I have a readme file in here with abstract, installation, instruction, downloads, instruction, usage, and network diagrams, the basic block diagrams that will be helpful for understanding my project. I'm still uploading the required files in here. It's taking a lot of time. Still 12 hours left. And this is in the project structure. This is the main file, project.ipython file, which summarizes all my work in here with abstract, introduction, literature review, experiment section, discussion section, visualization of everything, and finally a conclusion. So this is the main file that I use for project demonstration. And we have some files. Okay, so now I will go through my project implementation in here briefly, just to give you an overview of my research. So the objective of my research initially, when I started out with this project about a month ago, my initial objective was that I want to make a new neural network architecture, starting from the original architecture of DOPE. Now DOPE stands for Deep Object Pose Estimation. It's a 3D pose estimator algorithm. In short, DOPE detects the 3D bounding box surrounding my target object, and from there we can calculate the 6 degree of freedom pose of my target object. My objective was that, starting out with the original architecture of DOPE, I will basically change the neural network design and try to optimize the neural network design and come up with a new network structure that would be faster than the original structure, and also it will lose comparably it will not lose that much accuracy in prediction capability. It will not lose that much prediction capability. So that was my objective. And eventually I did not come up with a single neural network architecture that would work very nicely, and I will describe why I couldn't do that. Instead, over 1 month, I have come up with I have experimented with different designs and tried to present the difficulties I have faced, or the conclusions that I drew from different designs, or trying out different experiments. So this is, for example, another neural network architecture, DOPE 2. There is another one, DOPE 2.1. There is another one, DOPE 2.2, but it's basically same as DOPE 2.1. That's why I didn't give a separate image for this. And then another image in here, which is called ResNet Pose. This is a completely new architecture, different architecture from the original architecture. As you can see, is based on ResNet 34 architecture, and this is a close-up shot of the same ResNet Pose. So eventually what I ended up with is that I experimented with these neural network architectures, DOPE 2, 2.1, 2.2, and then also ResNet Pose, and I tried to present my conclusions from these neural network designs and the things that I learned. So for introduction, basically I describe in here what is 6 degree of freedom pose, and I take the reference from this website. It's a leaderboard for object pose estimation. And then I say that why I have chosen Deep Object Pose Estimator. That is because I have been working with Deep Object Pose Estimator. I'm not actually working, I've been implementing in my research. I've been using this DOPE architecture in my research for, I think, for 1 year, but I never looked that much into details about this neural network structure. I wanted to learn more and also use the knowledge that I got from this course to basically understand what's going on inside in here and try out different other things. So in here and here I say that what was my original objective and what I ended up with. Now in here for literature review, I did not put paraphrase already existing literature reviews. I am referring to this paper, which is the current state of the art in deep object in pose estimation, among pose estimation algorithms. It's called DPOD. It has a very nice and clear description of the related works on 6 degree of freedom pose estimation, and I'm basically referring you to this part in here. And then if you're interested, please look into this paper. Now for experiments, before going for experiments, I will just show you one more thing, is that when I get to describing different neural network architecture or different experiments that I've done, you will see that I have put video links in here. So you will see that, okay, this the video is about dope pose estimation overview, a high level overview. The video spelling is wrong. Then dope original architecture overview. If you click in here, you will find a YouTube video where I have drawn the log diagram and shown how this neural network architecture works and what it calculates, and how do we calculate the loss and use gradient injections or those things. So I've made individual videos about all these neural network architectures and not the experiments, but just a high level overview of the designs that I have come up with in here, or experimented with. Okay, now let's go sequentially. So at the start of experiments section, no, not experiments, at the start of experiments section, let's just import the dependencies, then load the image. So in here you can change this from 0 to 15. These are the test images. Whatever image you choose, later on in the project file, this file will work on this image. Now the first challenge that I faced while working on this was training time. That is because this is a 92 layer dope. Original dope is a 92 layer convolutional layer, and it has about 50 million parameters. So the first challenge was that the first thing that I had to decide is that which object do I want to train on, because if you look at the data set, the original data set, it has, I think, about 20 objects in here, and I could not conduct my research on all 20 objects. Because training this network for a single object of this would take me about 6 hours or more with my setup. The original authors actually used a DGX system, NVIDIA DGX system, probably a $200,000 GPU server for 2 or 3 days continuously to train the neural network, and I could not obviously compete with them. I have only one GPU, or I have 2 GPUs, but I can use only one of them at a time. That was a problem, and I had to face. So I chose this object in here, which is a spam meatcan in here. I wanted to conduct my experiments for only this object. So this is the same object as this one. So that's the first decision I had to make. The second problem was that even if I did choose this object, single object, it still took me about 6, maybe even more hours to train my neural network on 3000 images, and that's a huge amount of time. And over the past 1 month, I have probably tested over 30 variations of network architecture, and every time, if it took me 6 hours or more, I could have never finished this in time. So I had to come up with another idea of doing this hyperparameter exploration research quickly. So I came up with this idea in here, which is something called DevBatch. So what I did is that I took 16 images out of all these out of the entire data set, like this, and initially I just tried to overfit my neural network on these 16 images only, and if I see that my network architecture starts learning something that is perceivable, so something that makes sense, then that means my neural architecture will eventually learn something. But if it fails even to overfit on these 16 images only, that means there is something wrong with the design and it will not work. Maybe the learning rate is wrong, or something else is wrong. So this thing was actually super helpful in getting this research forward. I wasted about 2 weeks trying to train without this DevBatch, and once I once I started using this dev batch, the progress was much more smoother. So now let's move on. So now I'm going to show you, demonstrate in here that what is the benefit of dev batch. So what I did was that I took the original architecture of original dope, and then I trained it for 60 epochs, and in here I'm showing you this loading the 60th epoch weights. Now the 60th epoch of dope is loaded, trained on only the 16 images, and this is the output. This is how the output looks like. Again, if you want to understand what is belief maps, please refer to the video links below. So it is in short, what these maps represent are predicted locations of the vertices of my target object, or 3D cuboid, target 3D cuboid. So if you say, look at in here, you will see that it is the final outputs are starting to represent something that is similar to the image. In the center you have this object. You will see there is a bright blob in here. There is a V-shaped edge, I would say, in the image in here, V-shaped corner in here. As you can see, there is a V shape in here. Also there is another V shape in here. You will see another V shape in here. That means the network is starting to learn something. If you look at the belief map outputs, you will see that the network has started to learn something. So this is how I can get a guess that if I use just 16 images, the network is trying to learn something that is useful, that is understandable, and that means the network will eventually converge. And once I see this proof that it will eventually converge, then I take the risk of training it for maybe 6 hours, maybe 12 hours. But unless I see this proof using dev batch, I do not go forward with more experimentation. And let me just show you that the other case, the cases where you, after 60 epochs with the 16 images, you get nothing useful, or you get nothing that makes sense. So and here I load another network which is named ResNet-Pose, and again I train this network also on 16 images, and this is how the output looks like. So this is the output, belief map outputs. Now this was supposed to, through this map, the network was supposed to indicate to me that where it thinks the highest probability of a vertex point of a 3D cuboid might exist. So it was supposed to show a very bright spot somewhere in here. By the way, just for reference, these belief maps, the ground truth belief maps, looks like this. It will have complete black all over, and it will have a single bright spot at a particular pixel, and this pixel represents the predicted location of the vertex, the 3D cuboid vertex. That means by vertex I mean these points. These are vertex of the cuboid, or corner points of the cuboid. So this is how it should look like. And you see that if I look at the belief maps, it's absolutely noise. There is absolutely nothing perceivable in here. That means there is something wrong with the neural network architecture, and if I take a risk of training this network for 12 hours, maybe 24 hours, it will be a bad risk, and I wouldn't go forward with this risky experiment and waste my time. So that's how this dev batch really helped me to move forward with this project, and I thought this would be a very nice idea to include this in the start of my project presentation in here. So once we are clear about how belief maps look like, and how I have progressed through dev batch, now in here, in the later stages, I present about, I think, 4 or 5 neural network architectures which I have found interesting. Just to mention, I have worked on this for about a month, and if you look at my log, is started from 4 months, April 4th, and I'm ending up, I think it's May 1st. So I've been working continuously on this project, and over the time I've worked with about 30 structures, designs. Most of them failed, but these are basically representative of the works that I've done, sort of, and here I am showing you the those architectures. So again, if you so first thing was that so let's go for the first experiment. So the usage of VGG pre-trained network and progression of training. This is what I want to focus on. So if you look at the original architecture, again, if you want to understand, let me just put it in another tab. It's just annoying. Okay, if you want to understand about this, you can watch this video, where these videos where I've explained the basics. In short, basically, dope architecture first. In here, it takes the first 10 layers of VGG 19, and then later on it adds up these layers in here. So in the code, when I first cloned the project about a year back, it had this bug in the project that the pre-trained feature was hard-coded to be false, so it was never training with pre-trained weights of VGG 19. So that was a problem. Once I started this project a month ago, I found out this issue on my own, and then checked and then repaired this. And I wanted to see like it was an interesting experiment, that what happens when I train this same network with pre-trained VGG and without pre-trained VGG. And that's what I demonstrate in this first part. And then I also show the progression of training. That means, how does the training evolve with time? How does the network gets more and more confident with time? So in here, first I will load the models. Model 1 will be is network trained on trained without pre-trained VGG, and model 2 is trained with pre-trained VGG. And in here I have printed out the structure of dope architecture. Now, one thing I wanted to mention, that why I chose PyTorch is because my base architecture dope was implemented originally in PyTorch, and I wanted to just focus on PyTorch to get more skills on it, rather than exploring other great frameworks like Keras or TensorFlow and just getting basic idea about them. I wanted to get deeper into PyTorch. Anyway, so now let's look at the vertex visualizations. So in here I'm showing you the predicted location, or where the model thinks the vertex exists. This left column represents the ground truth. This is model 1's predicted belief maps or predicted vertex location, and this model 2's predicted vertex locations. The bigger the red dot in here, the more confused the neural network is, and the smaller the dot is, the more confident the neural network is. And again, both neural networks have had been trained with for 60 epochs on same number of images, that is 3000 images. By the way, all the networks that I will be presenting from now on will be trained on 3000 images, because I was confident that this would be a good experiment to run. So anyway, so this is the ground truth. So this is where the vertex point lies. This is model without pre-trained VGG predicts the location of this vertex point, and this is the model which is which uses pre-trained VGG net predicts the location of. So if you look at the size of these dots in here, let me just focus up a little bit. If you look at the size of these dots, you will see that this is much bigger than this. That means there is a clear indication that model trained with VGG, pre-trained VGG weights converges much faster than it would converge if I didn't use pre-trained VGG. And the same thing repeats in belief map 1 as well. If you see, this one is much bigger than this one. That means as this is smaller, that means this is where the this model is much more confident in predicting the position of a vertex point. So this I sort of use these visualizations to get more intuitions rather than just showing some graphs or numbers. I think visualizing things makes it more observable. And in here, if you see the belief map 2, the ground truth is on the right. However, model 2 predicts it wrong, and also predicts the prediction is very confused. The dot is very big. On the other hand, this one it predicted it quite right. Although this is yes on training image testing on training images, but still this gives a good idea about neural network designing, that what works and what doesn't work, what converges faster, what converges slower, what doesn't converge at all. So this is a demonstration of this is how it is a demonstration of basically the how should I say, the usage of pre-trained VGG and not using pre-trained VGG in here. Now I will show you the predicted belief maps again. This is how the ground truth belief maps should look like. It will each belief map should have black all over and a single white spot where it thinks the highest probability of a vertex point being existing is the highest. Okay, and then this is the visualization of the belief maps from the first model. As you can see, the belief map is very confused, like it is detecting, like yes, you see that the highest probability exists in here, which is right, but it also shows a lot of confusion all over this place. Same thing goes for belief map 2. It's much more confident, much better than belief map 1, but still you see there are some ambiguities, there are some confusions in the neural network design. Now let's look at belief maps generated by the model which was trained on VGG for the same number of time with the same learning rate. You will see the belief maps are very confident. They're so confident they look like they're the ground truths. There are no confusions, almost no confusion at all. They have a single very bright spot at the correct point. Same thing repeats everywhere, which is a clear sign or clear visualization of the power of using transfer learning and pre-trained weights. I thought this would be a nice demonstration, and I decided to include in my project report in here. So now that we are clear that using pre-trained weights is definitely better than not using pre-trained weights in the backbone network. From now on, whatever network I design, I decided to use pre-trained weights always. So every network that I will be presenting from now on will have pre-trained weights. Now the second network, so now I start to modify the original DOPE architecture, which is this one, and I come up with something called DOPE 2. Again, I have explained all these things in the videos. I have put videos for all my experiments. So everything explained in videos with writing. Okay, so in short, as I'm recording this video, let me just tell you what is the main change. So DOPE original architecture has two chains. Single chain, this one chain, this is used for calculating belief maps. Another chain in here which is used for calculating affinity maps. What those are, I have explained that in video. Basically, these belief maps give us the location of the predicted vertices, and these give us information about which vertices belong to which object or which vertices belong to which centroid, because these will just give you some dots, that's it, but they will not bind them together. They will not give you information that okay, these several vertices belong to a single object and they make up a single object. So you sort of need a direction information, and that's what these red affinity maps give you. And so now I'm going to talk about my first modification. My first idea was that I will just get rid of this chain entirely, because this is another 40 layers of convolution. I will just get rid of this 40 layers, and I will make this layer learn to do both the jobs. So instead of producing 9 outputs or 16 outputs individually through a chain, this entire chain will produce 25 outputs. So that's what I've done. I've just eliminated this part and assigned this same job in here, as you can see in here. So this will have a single chain of cascades, and it will produce both the belief maps and the affinity maps. In short, that's the thing that I've done. I wanted to experiment with. Okay, So let's just start out with both 60. So again, model 1 is the dope using pre-10 weights, and model 2 is dope 2, dope 2 with a single chain of maps. And in here I am printing out the dope 2's architecture in here. If you're interested, you can look into it. And at the end I also print the number of parameters in here. So if you this also, I will focus on this as well. I will focus this on later on. So it has about 28 million parameters, and let's see how many parameters did dope had, original dope had. So original dope had 50 million parameters. So that's about almost not half, but somewhat lower. So so that was my objective. I wanted to use the existing weights, about those 28 million weights. I wanted to make them to do the same job as dope. I wanted to see whether it can be done. Now let's vertex prediction visualization. Let's do vertex prediction visualization. So this is the left one is ground truth. The middle one is dope, original dope with pre-10 weights. Again, 2 chain in here, and this one is dope 2 with a single chain, also using pre-10 weights. So if you look at in here, you will see that this is almost as good as the original dope. But still there are confusions, as you can see in here. Also, yeah, in here this confusion is more than the original dope. So there is a clear indication that we have lost some capability, because it has to be loss of capability, because we are it's not a convergence problem. As we have reduced the number of parameters in here, that means it is an easier problem to converge compared to original dope architecture. If I had increased the number of parameters, then I would have said that okay, it is just taking more time to converge. But as this has lower number of parameters, it should convert faster, overfit faster compared to the original dope architecture. But it is not. That means the problem is in the capability. So I have decreased the total capacity of the neural network architecture, and that is more demonstrated when I show you the belief maps. So first I show you the belief maps predicted by I think okay, sorry, yeah, I jumped a little bit, I'm sorry. Okay, so let me show you the belief maps. Okay, again, what happened? Okay, so this is the belief maps predicted by the original dope architecture. As you can see, they are very confident, and this is what the belief maps produced by dope 2.1 looks like. Sorry, dope 2 looks like. It's very confused. It is almost if I want to make this one look similar to belief maps produced by dope 2, let's just reduce the epoch number. So for dope, original dope, let's choose epoch number 20. So now I am showing epoch number 20. Epoch number 20 for original dope, and epoch number 60 for dope 2. Now you will see that dope at epoch 20, the predicted maps of dope at epoch 20 look similar to dope 2 at epoch 60. That means that dope has converged up to this point, or at this standard, by epoch 20, whereas this one has not been able to converge. as confidently as dope original dope architecture. So this is this is also a demonstration of the training progression. So yeah. So the conclusion that I drew from in here is that once I decrease the number of parameters, I decrease the capability of neural network, and this still works, and it is actually 1.5 times faster in my testing, but still I've lost some capability. So that was an interesting observation for me. Now I wanted to optimize dope's architecture, dope 2's architecture even more, and again I have explained this in my video. So in short, let me just show you what I mean by make it more efficient. So as you can see in here, we have after VGG we add in the dope 2 we add 2 convolution layers just as original in here, and then we have cascades, each with about 5 to 7 layers of convolution. These cascades from cascade 2 to 6 have 7 layers of convolution. Cascade 1 has 5 layers of convolution. In total you have 40 layers of convolution in here, and you have 12 layers of convolution in here. So my hypothesis was that there is an inefficiency in design. That is because once I calculate this 128 image features, then I pass them along through all of these cascades, and each of these cascades, my hypothesis is that the first few layers of each of these cascades are doing the same job, just like convolution layer works, convolution neural network works. As we know, convolution neural networks, once you give it an input image, the first several layers actually work to come up with some basic features like edges or corners or something like that. So in short, they do some basic operations. So that's my assumption is that the first few layers of each of these cascades are doing the same job. So my question is, why am I doing the same job 6 times, whereas I can do that same job 1 time if I add that feature in this block? That's what I do in here. So in short, I reduce the size of these cascades and increase the size of this cascade in here. So not cascade, this block. So I name this term differently. I call this the first 10 layers taken from VGG. I call them VGG block, and I name this block as feature block, and I add 10 convolution layers instead of 2 convolution layers, and in the cascades I reduce the number of convolutions from 7 to 4 in each of these cascades and try to do the same job. My objective was not to outperform dope. My objective was to see if this experiment, or if my hypothesis is right or wrong, or at least try to get a idea of whether my hypothesis is right or wrong, just to get a more deeper idea of deep neural networks. So let me show you the performances. So now I'm experimenting or comparing dope 2 with dope 2.1. Again, dope 2 is just a single network architecture modified from original dope, and dope 2.1 is a more modified version of dope 2, in which I add this feature block and reduce the size of the cascades. Here I have printed out the network structure. As you can see, I have added a feature block in here with 10 convolutions, and the cascades are much smaller than before. Now let's see the visualizations of predicted vertices. So this is the ground truth. This is using dope 2, and the last column is dope 2.1. If you look in here, if you compare the sizes, they are quite similar. Actually, this the size of dope 2.1 is actually smaller, and it looks as if dope 2.1 is actually more confident in its prediction compared to dope 2. If you look at in here, it's clear indication that dope 2.1 is actually better than dope 2. But what if the parameters have increased? Like there is a design flaw and increase the number of parameters. So let's also check the number of parameters. So it's about 15 million parameters for dope 2.1. Let's see what about dope 2. 28 million. So I have actually reduced the number of parameters, but I have been able to train a neural network that is more efficient than a network that has almost double the number of parameters. So that was a nice experiment for me to see that I was able to design it more efficiently. Of course, my results are not conclusive. They're still they're just visual indicators, but still it was a nice experiment for me. Now let's look at the belief map visualizations. So this is the belief map visualization for DOPE 2, and this is the visualization for DOPE 2.1. So if you see the visualizations of DOPE 2, you have a lot of confusions, and let's see DOPE 2.1, you also have a lot of confusions. But if you look closely, I think the DOPE 2's belief maps are in general brighter than DOPE 2.1's. If you see the DOPE 2.1, no, actually they are quite similar. Yes, they are quite similar. Okay, so the conclusion that I drew from in here, that I am getting almost equivalent performance or equivalent convergence capacity from both the models, whereas DOPE 2 is working with about 28 million parameters and DOPE 2.1 is working with 15 million parameters. So in short, I have been able to, at least in I've got the visual indication that I have been able to make the neural network architecture more optimized, have been able to optimize the neural network architecture. So this is another experiment that I wanted to show you in here. Now after DOPE 2.1, I actually started out with another completely different style architecture. Not completely, at least the backbone is different, which I call ResNet-Bose. So now I'm going to talk about ResNet-Bose. Now ResNet-Bose is a same cascade based system, but it is based on ResNet 34, which I have shown in here. I don't know if you can see very well. Let me just focus up. So it's based on ResNet 34 architecture. Actually, I do not need to show you from here. I can show you from here actually. I'll bring it up. Okay, so this is the ResNet 34 architecture. As you can see, the residual connection, this is layer 1 in terms of how PyTorch these are defined. This is layer 1, this is layer 2, this is layer 3, this is layer 4, and finally you have the fully connected layers. So what my objective was that I wanted to use as much transfer learning as possible. That's why I decided, okay, let's just use the 34 layer convolution layer, ResNet 34, which is very well known for its very nice performance. So, and try to just sort of sample the image features that is being generated at different stages and use that image features to implement the cascade system and come up with output 1, output 2, output 2 and output 3 and 4, 5 and 6 for the belief maps and the affinity maps. So in short, what I am doing is that I am sampling the image features from in here, then I am sending them to the cascades. The cascades are calculating the 25 channel output. The cascades are, sorry, I'll hide this. It's very annoying, I'm sorry. Okay, so the cascades are again taking the image features and they are calculating the feature maps. The cascade 2 is getting feature decisions from the previous cascade and then basically refining its decision. Cascade 3 again is getting the decisions from the cascade 2 and refining that decision. All along they are all receiving the same image features, from layer 3. Then from layer 4 I take more complex features and pass them on to cascade 4, 5 and 6, and I also pass around the decisions made by cascade 3 to cascade 4, and then it refines that decision and I get my output 4. Similarly, eventually I get my output 6. So this is a completely different style, not completely different, but a different approach to this entire problem. I wanted to see what happens. Another thing I wanted to highlight in here is that inside the cascade now I do not have a simple convolution layer architecture like conv then batch normalization or something like those. Instead I use basic blocks. Now what are basic blocks? Basic blocks are these blocks. Basic blocks are like two convolutional layers, and you have identity connection from input to output. So as a result, now I will have residual connection or identity connection in here. As a result, whenever I do gradient flow, so let's say that gradient is coming from here in this direction from here, then it will come in here, then it will have a very nice gradient flow due to the identity connections, and the gradient flow will be direct. So there will be very low loss of gradient flow. The gradient flow will be very easy, and then you also have residual connections all towards absolutely the last layer. So we have residual identity connections starting from the very first convolution layer to the very last convolution layer. Everything is connected with identity connections, and I thought that would be a nice feature to have, especially because this is a huge network, 92 layer convolution layer for the original dope. And if I'm going to make a convolution layer that is about this deep, then having residual connections or identity connections should enable me to converge faster, which would be a significant gain when it comes to this sort of research, high time consuming research. Now I'm just going to show you the experiment results in here. So I'm loading up ResNet architecture in here. I've shown you, printed out the ResNet architecture in here. Now let's look at the predicted belief maps. Again, this is trained on 33,000 images. Now I want to emphasize one thing, is that before I started working with ResNet, this architecture, I tried this network on my dev batch of 16 images and it failed to converge. So from there I had an indication that this will eventually, even if I train it for on 3000 images for 60 epochs, it will fail. But still, this is a good representative of the failures that I've had in this project, and I thought about including it. Now in here you see that after training it, and this is how the belief map visualization looks like. You see it absolutely has nothing. It has learned absolutely nothing in here. They're all garbage, and this is where the model thinks the highest probability of a vertex being present is, and you see it's absolutely garbage. So the network has failed to learn anything. So after this I thought, okay, what's the problem? Like, is the problem that I've used residual connection, or the problem is that I've used batch normalizations? Because ResNet 34 and all these blocks in here who have batch normalizations in them as well as residual connections in them. So I needed to experiment whether which one was causing this problem. So I tested out with batch normalization, and for that what I did was that in DOPE 2.1 architecture, I used the same DOPE 2.1 architecture for which I already saw some success, and then I added batch normalization in between each convolution layer and ReLU layer, and from first to last everything was everywhere batch normalization was added. Another major change was that I also had to add batch normalizations in here, but if I did that I could not use the pre-trained weights, or it would be harder to use them. So instead what I used was that batch normalization layer added version of VGG 19, which is named as VGG 19BN batch normalization in PyTorch model soup. So from there I replaced this VGG tail layers with its batch normalization added version. So every convolution layer now is followed by a batch normalization, and here are the results. Now I'm going to talk about the results. Again, I have explained these layer visualization or design modifications briefly in these videos. You can check them out if you want. Okay, let's load the network. In here, model 1 is dope 2.1 and model 2 is dope 2.2. And in here I've printed out the network, and as you can see there is a conv batch normalization that ReLU. Again, conv batch normalization ReLU. Everything has a batch normalization now. Now let's look at the predicted belief map. So first I am showing you the dope 2.1, for which I already saw some success in terms of optimization. These are the belief maps. These are the belief maps. Okay, I can focus up. These are the belief maps. And okay, where did it go? And these are the belief maps by dope 2.2. As you can see, it has been able to learn. I do not know whether it is better or worse, but I know that it is possible to train a neural network with patch normalization added from end to end. So I know it will work. But definitely one thing is quite clear to me, that it is harder when you have batch normalization. It's harder to train when you have batch normalization, at least in here. Although in theoretically, when we add batch normalization, it becomes easier for a neural network to learn the patterns in the image features, because we are normalizing the image in the input features to each layer, right? But in here, my intuition or my conclusion was that once I added the batch normalization, I added more and more parameters, trainable parameters, because we know that it just does not, batch normalization just does not do zero mean and unity standard deviation. It actually learns the deviation, it actually learns the mean, which works best. So for each individual pixel locations, or for each individual image feature location in spatial domain, I'm adding I'm adding at least 2 parameters as far as I understand. So I'm increasing the number of parameters to learn, and that is what I think is making the convergence problem slower, convergence problem harder for me. That was my conclusion. So from my ResNet pose, now if I think about ResNet pose, so definitely the problem is not batch normalization. The problem is my residual connections. So now I'm going to go into my discussion section, the things that I've learned, things that I thought that I should mention, although I could not show them numerically or visually, graphically in here, but I thought they are very nice things to add. The first important lesson I learned the very hard way was the learning rate is the most important hyperparameters. I've learned this, I've heard this in several deep learning courses, but I did not realize its significance until I worked on this project for a month. So I had wasted about 2 months, just 2 weeks, trying out different neural network architectures, but during those first 2 weeks nothing would converge, or most of the times things would converge, and I decided on my dev batch, and I decided that okay, there is something wrong and it will never converge. Later on I realized that whenever I try out a new neural network design, I must first set the highest learning rate that the model can bear or tolerate. So that's something I didn't do, and once I started doing that, whenever I had a new neural network design, the first thing I decided on that what is the highest learning rate this model can tolerate. And once I start doing that, then it was easier to do the hyperparameter optimizations. And I also realized that many of the models that I had eliminated as it will never converge during the first 2 weeks would have actually converged if I had chosen the learning rate properly in the beginning. So that's an important lesson I have learned. I'm pretty sure that it will come in handy in later stages of my career. Now the second thing was that a lesson that I learned was that using adaptive learning rate decay is harmful during development stage. So another problem that I faced was that once when I was facing problem with learning rate, I decided to do something else. I decided to use adaptive learning rate. The adaptive learning rate works in this way, especially this method, is that whenever the loss curve reaches a plateau, then the learning rate is decayed by 10 times. So I had too much faith on this system, and what I started doing is that at the beginning, from epoch 1, I chose a ridiculously large learning rate, maybe 0.01 or 0.001, and then just I started the training process and just did my other work. But once once the training was done, I saw maybe all of the times, that network never learned anything useful. So I realized that when we start the learning process with a very high learning rate, you will see a spike in loss for maybe an epoch or two, and at that spike the weights are so much messed up that eventually, even if you get your loss to go down, it will never learn anything good. So the lesson I learned after this was that, okay, you must always find out the highest possible learning rate, highest tolerable learning rate for any new design, and do not use this adaptive learning rate, because I think this adaptive learning rate gives us a false sense of security in terms of training, and we do tend to neglect the power of choosing a proper learning rate. So in my opinion, this should be used, but you use it when you want to eke out like every bit of performance out of your model, not during development stage. So once you have decided on your neural network structure, you have decided on the highest possible learning rate, then you use these methods. It will be you can use this method safely. But at the development stage, this is a disastrous thing to do. Okay. Now another thing that I wanted to talk about was the pain of the problem of slow experimentation time. Like for every iteration, I have to wait 3 hours or 6 hours. Now, how could we overcome that? So this is my computer specs. I have an Intel i7 4th generation i7 processor, 3.4 GHz with 8 cores. I have 2 GPUs in my machine. One is NVIDIA Titan Xp, another is Titan X. My first objective was that, okay, now that I have a good machine, I wanted to use both the GPUs simultaneously to speed up my work. So I started using something called data parallel from PyTorch. What data parallel does is that it distributes the training system on multiple GPUs, and it usually speeds up your training. But what I learned is that data parallel works on a protocol called master and slave, and the data overhead, in short, is so high when you have only 2 GPUs that your speed gains are actually negative. That means your training time is actually slower than if you had trained your network on a single GPU. So I had to abandon this process. Now next, what I did was that run two training of 2 networks on 2 individual GPUs simultaneously. Then I realized I have a bottleneck not on GPU, I have a bottleneck on CPU. So the thing is that whenever I train my neural network, I would see the CPU usage go to 100%, and the training time for each of the networks would double compared to if I had trained them individually. And that means that the data loader, the CPU is the data loader, it loads up in my input images. It's not fast enough. It does not have that much capability to load the images fast enough for the GPU to process. So, and it actually reaches a bottleneck. So the bottleneck was CPU. So this was an important observation for me, because although up to this point I had believed that GPU is the only thing that you have to worry about when it comes to deep learning research. But now here I realize that, okay, now CPU is also very important, because this identification told me that I never actually reached the highest speed capability of either of my GPUs because of my CPU bottleneck. Probably if I had a better CPU, the 3 hours training time on a single GPU might have come down to 1 hour or maybe 2 hours of training time. I don't know, but I would never know unless I change my CPU now. So this was an interesting observation as well, and I thought about including it in here. Now again, another lesson was that use dev batch for data exploration. I've already explained that earlier. And then pause and continue large training sessions. So at the beginning of my research and also in other parts of my own research, I sometimes have to train a neural network for 2 or 3 days. So I added a feature in my training code which you can look up in here. I added a feature in my training code that lets me break out of a training session at any time without losing any sort of training data, not training data, training log data. And later on, once I have done with my other works and I have my GPU or CPU free, I would just say that continue the training from the point you left it, and if we just pick up from there and continue training. And this actually helped me make my usage of my computer most efficient, and probably literally I was running my computer for 30 days as much as possible, almost every hour of the day, and that was actually pretty fun. I'm a little bit worried about my electric bill this month, but it was fun. Next was that the final conclusion is that it's a much difficult problem to solve than I have anticipated. So at the beginning of this project, I thought, okay, let's just do it. Let's just come up with a new neural network architecture will be better than DOPE, and let's do a publication. But once I went inside, I understood that I threw myself down a rabbit hole, and it's not really that easy to come up with a neural network architecture. The main problem is it takes a huge amount of time, and it also takes a lot of intuitions and deep understanding of deep neural networks. So in here, at this final discussion stage, I present the number of parameters for each of my designs and try to come up with another intuition. So DOPE, the original DOPE parameter count is 50 million, DOPE 2 has 28 million, and DOPE 2.1 has 15 million, DOPE 2.2 has 15 million again, almost the same as this one, and with a very slight increase, almost non-existent. And then ResNet pose parameters, it has 79 million parameters, and that's what caught my eye, and that's what I wanted to focus on this last discussion session. So after printing out the number of parameters in my ResNet pose, I understood that I had made the convergence problem for my ResNet pose architecture so hard, even compared to the original network architecture of DOPE, that the model was never able to learn anything. Converging 79 parameters to their optimum value, optimum position, is very hard compared to optimizing of 50 million parameters. So that's something, that's a thing. So that's the thing I understood from here, from this visualization. And my objective is, in the later stage in my personal research, probably I will try out with another ResNet pose architecture with lower number of parameters. I know I did some mistakes in network designs, especially in the cascades. I could have easily turned the number of parameters down, but I just ran out of time and I didn't want to continue this research anymore. I wanted to focus on my other projects. So this is a conclusion I drew, that this would have probably worked. Residual connections will also work, but it's just that my network design was wrong. So this also gives me an idea that okay, how we should diagnose when something doesn't work. We should also see the number of parameters. We should also always check the usual suspects. So this is also one of the usual suspects, the number of parameters. So yes, this is my last discussion, and for conclusion is that in this project I tried to modify the network architecture DOPE and come up with an experiment with its neural network design to get a better understanding of deep neural networks, and probably, if possible, come up with a very good neural network architecture. And with that desire, I tried out with these neural network architectures, DOPE 2, DOPE 2.1, DOPE 2.2, and ResNetPose. And I have also presented why I have used DevBatch and why their visualizations, and I have also shown you the the usage or the advantage of using transfer learning when it comes to just for even if you are talking about just 10 layers, it makes a huge difference. So, and yes, basically I learned a lot about deep learning, PyTorch and Python just in 1 month, over the past month. I'm really happy with the things that I've learned with the project, and I really thank you for checking out the video. And with that, I'll conclude my presentation. Thank you.